So you guys have worked pretty extensively using stoichiometry in order to determine a limiting reactant. But there's actually an easier way to set up a problem, a limiting reactant problem, if we're given either moles or just pressure. Okay, so I'm going to introduce the concept of ice charts. We're going to use ice charts extensively in Big Idea 6, but I wanted to introduce it here for you to be able to see how to actually do a limiting reactant problem without actually having to set up all the stoichiometry of it. So I'm giving you a problem here. I tell you you have 1 mole of hydrogen and 1 mole of oxygen, and I'm asking how many moles of water will form. So I'm going to write out my reaction right there. Okay? For every 2 moles of hydrogen, 1 mole of oxygen reacts and 2 moles of water are produced. Then I'm going to create my ice chart, ICE. I stands for initial. So what is my initial amount of hydrogen, oxygen, and water? Well, based on this problem, I have 1 mole of hydrogen, I have 1 mole of oxygen, and I don't have any water, so it's going to be 0. Okay. All right, C stands for change. How will this change? Well, I know I'm going to lose hydrogen and I'm going to lose oxygen in order to form water. How do I know that? Well, I don't have any water to start with, so I can't lose any water. So what you do for your change is you are going to change it. So for example, for hydrogen, you're going to lose a specific amount of hydrogen. And we don't know that specific amount yet, so we're just going to represent it with an x. So it's going to be minus 2x because there's a 2 in front of hydrogen. Okay? For oxygen, it's going to be minus x. And for water, it's going to be plus 2x because there's a 2 coefficient in front of water. All right? Not too crazy? All right, here comes the hard part. We have to figure out what my x is going to be. Okay? So let's say, for example, I look at this problem and I say, okay, I'm going to assume all of my oxygen is going to react, meaning the x for oxygen is going to be 1.0. Well, if all of oxygen is consumed and my x is 1.0, the end concentration, E, the end, at the end, the amount of oxygen I would have would be 0 moles, right? So I would have 0 moles of oxygen. Fine, that's what I assumed. I'm assuming oxygen is my limiting reactant. Well, how much hydrogen would I have left? Okay. Well, if my x is 1, I would have 1.0 minus 2. That would give me a negative number. That doesn't work. So oxygen clearly is not my limiting reactant. Let's instead assume that I have 0 moles of hydrogen left over. Well, what would my x be then? 1 minus 2x equals 0. That would give me an x of 0.5. Let's see how that works. So I would have, if x is 0.5, then I would have 0 of hydrogen left over. I would have 1.0 minus 0.5, so I would have 0.5 of oxygen. That works fine. I don't have any negative numbers. So that is what my change is going to be, my x. So when this is done, I'm going to have no hydrogen. It's my limiting reactant. I'm going to have 0.5 of oxygen, and I'm going to have 1.0 moles of water. Okay? Then what I could ask next is, well, what happens to the pressure then? How does the pressure change as this reaction proceeds? So if you look at it, I started off at the beginning with a total of 2.0 moles of gas, right? 1 mole of hydrogen, 1 mole of oxygen. I finished with 1 mole of water and 0.5 moles of oxygen. So I went from 2 moles to a total of 1.5 moles. So I started off with 2 moles of a gas, and at the end of the reaction, I had 1.5 moles of gas. So common sense tells you if you're going from 2 moles of a gas to 1.5 moles of a gas, your pressure is going to be decreasing. So to determine the percent change, what you're going to do is you're going to find the difference between 2 and 1.5, so it changed by 0.5, and then you're going to divide it by the initial amount of reactant that you had. So 0.5 divided by my initial amount, which was 2, and that would give me a decrease of 25%. So let's look at another example. So here I start off with 2 moles of nitrogen, and I combine it with 1 mole of hydrogen, and I ask how many moles of NH3 will form. So here's my reaction. Okay. I have an ice chart, ICE. My initial number of moles of nitrogen is 2.0. My initial number of moles of hydrogen is 1.0. And my initial number of moles of NH3 is going to be 0 because I don't start with any. which tells me I'm going to lose reactant and I'm going to gain product. So my change for nitrogen is going to be minus X. My change for hydrogen would be minus 3X, and my change for ammonia would be plus 2X. Okay, so here comes the hard part. Let's figure out which is my limiting reactant, N2 or H2. So I'm going to first start with N2, because why not? In order for all of N2 to be used up, my X would have to be 2.0. If my X were 2.0, that would give me 0 for N2. If I then plug that in for the H2, I would have 1.0 minus 3 times 2, and that value would give me a negative number. So clearly N2 is not my limiting reactant, it's going to be an excess. H2 must be my limiting reactant. So you need to set up the problem. It's going to be 1.0 minus 3x equals 0. So what value of x would give me no H2 left over? Well, it would be 0.33 repeating. Okay, so if my x is 0.33 repeating, then I would do 2 minus 0.33 to get my number of moles of N2 at my endpoint, so that would be 1.67. Do the same thing for H2. Obviously, it's going to give me approximately 0. That's how I got 0.33 in the first place. And then I'm going to plug it in for NH3, 2 times 0.33, that would give me 0.66. Okay, so I went from having 3 moles of gas total, the 2 from nitrogen and 1 from hydrogen, to having 2.33 moles, right? I have 1.67 moles of N2 and 0.66 of NH3, which tells me that my pressure is going to be decreasing. I'm going from 3 moles to 2.33 moles. So to find the percent change, I'm going to take 3.0 and subtract from that 2.33, and then I'm going to divide that by 2.33. That will give me the percent change, which is about a 22% decrease in my pressure.